Today is a special day because this is the last lecture of the FP 101X series on functional programming. I hope that you enjoyed the ride and that you learned how to apply the ideas of pure functional programming in Haskell to your own programming language that you use at work. There's one thing that we have kind of waved our hands about, and that is lazy evaluation. And lazy evaluation is also something that is kind of unique to Haskell. There are other languages like Scala that do have some form of lazy evaluation, but the interesting thing about Haskell is that everything uses lazy evaluation unless you make things strict. And that's the topic of this lecture, is to give you a little bit of an introduction about the various possible evaluation strategies for functional programs. Okay, so up to now, we have not really looked at all at the details of how expressions are evaluated. We have done, evaluations on the slides where we kind of, unfolded definitions and so on, but we have not made this thing precise. And actually, Haskell expressions are evaluated with a fairly simple strategy. Okay, and the idea is that it's lazy. And think about you being a lazy person. The prototypical example is doing the dishes, all right? I hate doing the dishes, so I want to avoid unnecessary evaluation, all right? So I want to only wash a dish when it's absolutely necessary. Now, doing this lazy evaluation allows us to program with infinite data structures because we're never doing more work than necessary. So even if you give me an infinite list, an infinite stack of dishes, if I'm sufficiently lazy, I will only wash as many as I need. So you cannot catch me with that. And the other thing that we will see is lazy evaluation makes it easier to compose programs because there's never more work done than necessary. And this evaluation strategy is why Haskell is called a lazy language. And let's look at some concrete examples. And what we do to evaluate a Haskell program is to take a sub-expression. If we are evaluating a big expression, we're taking a sub-expression there, and we are kind of, evaluating that sub-expression. And in this case, say that we have a function definition square n is n times n. Now, if we have an expression like that, square 3 plus 4, then we can evaluate this in two ways. One is to first evaluate 3 plus 4 to 7, and then we use the definition of square, substitute 7 for n, then we get 7 times 7, and then we evaluate it to get 49. But another evaluation strategy is also to say, well, we take square of 3 plus 4, we substitute 3 plus 4 for n, so we get 3 plus 4 here, and 3 plus 4 here, and then, we evaluate the results, and we get the same value. But in that case, you might think, oh, but now we have evaluated 3 plus 4 twice. And as we will see, Haskell has some smart ways to avoid duplicating that computation. So let's look at the first sample, the first strategy. So we first evaluate 3 plus 4 to give us 7. Then we substitute the definition of square So n equals 7, so we get 7 times 7, and we get 49. Now let's do it the other way around. We take this expression, we instantiate n with 3 plus 4, so we get 3 plus 4 times 3 plus 4. Now we execute this guy to 7, we execute that guy to 7, and we get 49. Okay? So in this case, we have first applied square before doing the addition. But the nice thing is that the final result is the same. And now imagine that there were side effects in this code. Well, in that case, since we're doing the evaluation in different orders, the side effects might happen in different order and the result might be different. But since we're here in the pure world, it doesn't matter in what order you do these reductions. Okay? So that's a fact about Haskell, that if there are two different ways that both terminate to evaluate the same expression, then these will always give the same final result. And that makes it also easy to kind of refactor Haskell programs, because you can always substitute and massage things independent of where they appear. And that's because of this property. Now, we've seen two strategies to reduce our program, and let's talk about that in a more general sense. So what we do is when we're evaluating an expression, there might be many choices of sub-expressions that we can reduce. And we have seen in this very small example, we've seen this already. We could either first apply the definition of square, or we could first do the arithmetic on the arguments. Okay? So there are two basic strategies to decide which of all possible expressions to choose. And the one is innermost reduction, which says the innermost expression that can be reduced is always be reduced. And then there's the outermost reduction, where you take the outermost expression to be reduced. And of course, you can say, since this rule, we can also do random execution. We can pick any expression to be reduced, but that's not very systematic, right? And that makes it kind of, hard to, it's kind of nice to have a fixed strategy such that we can reason about its properties. And let's look at this example here, where we have a weird recursive definition. So we define loop to take the tail of loop. Now, what does that mean? Well, first of all, it means that loop must have type list. All right, and then so we take the tail of the list. So this is a list that chases its own tail. And let's evaluate the expression, give me the first of the pair 1 and loop. And let's compare and contrast these two reduction strategies. Notice that when we, reduce this guy, loop equals tail of loop. So let's substitute loop, so we get tail of tail of tail of tail. So this thing actually chases its tail, and it will never find an actual list that it can take a tail. So it will loop. But let's look at this guy. So the innermost reduction takes the innermost reducible expression and reduces that. So in this expression here, the innermost reducible expression is loop. So we expand loop into tail of loop. Now loop is again the innermost expression, and then we execute this. So this will not terminate. So this evaluation order is too strict. It kind of tries to evaluate the argument here of first, the inside this tuple, and then that diverges, and there's no chance that we can take the first of this pair. Now let's look at the outermost reduction. So in that case, we take the outermost reducible expression. That's first, it's applied to a tuple, which is a reducible expression. So first of a tuple A and B is A, it's 1, and we're done. All right? So this strategy gives us the result in one step, whereas the innermost reduction would never terminate. Okay, what are some facts here is that the outermost reduction may give a result when the innermost reduction fails to terminate. And this is what we have seen. And the second fact is that if for an expression there exists a sequence that terminates, then the outermost reduction also terminates. Okay? And it will return with the same result. So if there is any reduction sequence that terminates, the outermost reduction will always also terminate. So that gives a strong hint that the outermost strategy is not a bad thing. Okay? If there is any way that this thing will return a value in finite time, the outermost reduction will also terminate. Now let's look at a few other examples of innermost and outermost reduction. And there maybe we kind of, that will throw some doubt on the outermost reduction. And this is our familiar example with square. If we do the innermost reduction, we do 3 plus 4, 7. 7 times 7, 49. So this is done in 1, 2, 3 steps. But if we do the outermost reduction, we're duplicating that reducible expression 3 plus 4. So we're doing the work twice. Okay? So that's a fact that outermost reduction may require more steps than innermost reduction. But as we have seen, sometimes innermost reduction will not terminate. Here's the crucial question. Is there a way to have our cake and eat it too? And it turns out that there is. And the way we solve this problem is by using sharing. So when we substitute 3 plus 4 into the definition of square, we don't just copy that expression 3 plus 4, but we share it. So we have pointers to that expression such that when we reduce it once, it returned to 7, and now the results are shared, and then we get 49. All right? And that's what lazy evaluation is. Lazy evaluation is outermost reduction plus sharing. So lazy evaluation is like having your cake and eating it too. And Haskell uses lazy evaluation. Here's another example that shows the advantages of lazy evaluation by defining a recursive type of list, a recursive value, I should say, of list. The list is, of course, a recursive type, but we're looking here at a recursive value. So we define the list, the infinite list of ones, as ones cons ones. So let's unfold the recursion a couple of times. So we see that ones is ones cons ones. Unfold it again, so we get ones cons ones cons ones, etc., etc. So ones is an infinite list of ones. Now let's look at the evaluation of head of ones. Okay? And what we want to do is we want to compare and contrast innermost evaluation with lazy evaluation. And you can already guess what will happen. When we use innermost reduction, this is kind of the same example as I had with loop. So we are taking the innermost reducible expression, which is ones. We unfold it, we unfold it, we unfold it. So we never get around to taking the head of that list. Whereas this list is already in the shape where we can take its head. Okay, so it doesn't terminate. Whereas if we use lazy evaluation, head of ones, well, that's still not reducible, so we have to unfold this guy, so we get 1 cons of ones. Now we can do this, and we're done. Okay? So in this case, the result is 1. So in general, the slogan of lazy evaluation, think of doing the dishes, is we're doing just enough work as required to produce the final result. Okay? And so really, when we say that once is an infinite list, we're kind of lying, because once is not an infinite list. It's a potentially infinite list. Only when it's kind of expanded on demand. And it's not expanded eagerly to an infinite list. So it's just a recipe to create an infinite list. And if you would do this in a strict language, what typically happens is you would say this is once is defined using some form of thunk. So you put in a unit arrow somewhere to stop the evaluation because that function unit arrow is already a value. Now let's look at the next example here. We mentioned that lazy evaluation makes code more modular. And the reason is that it's because it does just enough evaluation to kind of make the next step. So let's look at take 5 of ones. That will return a list of 5 ones. Okay? And ones is really the same as this expression here, the infinite list of ones, and that also returns 5 ones. And again, the reason is that we have seen that take was defined by induction over the structure of the list. So every time that one's pattern matches on that list is evaluated just enough to kind of get the next value, such that we nicely terminate here. So this is the end of part 2 about lazy evaluation, and see you in a few minutes.